Okay, so our next unit is actually kind of a short little unit. It's really kind of an extension of, well, really going back to our unit on moles. Is going to be something called molarity, which we're going to introduce as solution concentration. So this next section, it's really kind of a standalone little mini unit, and it's only going to be 2 quick sections, so let's get to it. So for expressing concentration of something, and you guys in your life experience have noticed how certain things are more dilute than others. Concentration is really just a measure of how much solute is dissolved in a specific amount of solvent. Okay, we learned these terms last semester, so in case you've forgotten, the solute, right, is the thing that gets dissolved. So that's the thing that's going to be put into solution. Okay, and the solvent is the thing that it is being dissolved in. Oftentimes, that is going to come in the form of water, right, H2O, and that would make it an aqueous solution, right? We've learned that term. You've seen that a whole bunch. But just because something's in water doesn't mean that it's always going to be equally concentrated. The more stuff you put in there, right, the more concentrated it is, or the more water you add, the more dilute something becomes. Kind of in your example there of the tea being made on the left, right, we've got a lot more tea bags in the water, so it's going to be a lot more concentrated. It's going to have a lot more flavor to it versus the one on the right. Okay, it's a much more dilute solution. And so what we want to do as chemists is to come up as a way to quantify this value, right, to express it. And so that's what we're going to do. There are various ways to do this, and really one of them is certainly much better than the others. Percent by mass, that's used occasionally, but we are not going to use that here. So the equation, right, mass of solute over the mass of the solution times 100. That's an okay way of doing it, but mass really isn't a great way for us to determine just how concentrated something is because, well, things have different molar masses, so it's not really a great way of doing that. Percent by volume, we don't really use this a whole lot. This is often used to express the concentration of alcohol in alcoholic beverages. If you see things listed as ABV, alcohol by volume, that's what that is actually representing. So what percentage of it is alcohol over the entire volume of the solution? It's kind of helpful, but it's really still not a great way to determine the concentration of something, right? Things don't have the same densities, and so it's really not a great way of doing that. This one, though, right here, molarity, this is the go-to one that we are going to use for determining concentration. The moles of solute per liter of solution. We're going to come back to this guy right here. And molality, this is used occasionally. The more you go into chemistry, the more you're going to see it, but we don't use it a whole lot. Moles of solute per kilogram of solvent, we're not really going to use this one. In mole fraction, we may get more into this action. We talk about gas laws later on this year. So really the only one of these that's going to be used at all for this brief little section is molarity. So what is that? Well, molarity is the number of moles of solute dissolved per liter of solution. It's also sometimes called molar concentration. So the symbol for it is an italicized capital M. And it's kind of an important thing to note there that it is, in fact, in italics because this, if you're not being careful, can get confused with molar mass, right, which is that cursive capital M that we've been seeing since last semester. So those two things are different things, okay? This italicized M is molarity, all right? The units for it are moles over liter or moles per liter, or you can see it again as that italicized capital M. So either one of these three things here, either this, right, or if they want to shorten it, moles over liter, or simply if they just put an italicized capital M, that's another way of giving that unit. The concentrations are written as this. They look like, okay, these brackets, right, at the beginning and the front of our substance, and in the middle of it is whatever your solute is. So the thing dissolved goes in here, whatever that substance is. The example here, how you would read this, right, you're going to see this on your homework, is you'd say the concentration of calcium chloride, CaCl2, is equal to 0.150 molar. Okay, that's how you'd read that. Concentration of CaCl2 is equal to 0.150 molar. So that's how we read that. Down at the bottom, this equation on molarity, star this. You are going to use this a whole bunch. So right now, yes, this is a short little mini unit on molarity, but the entire next unit on acids and bases, you have to know how to do this. Okay, it is absolutely vital to know the equation for molarity, which is moles of solute divided by liters of solution. Okay, and if you want to simplify that, just simply moles over volume, right? And notice that the volume here has to be in the unit of liters, right? V has to be in liters. Moles are obviously going to be in moles, but we have to have it in liters. So if you see anything like milliliters, we then need to convert it to liters in order to plug it into the molarity equation. So just a heads up there, right? You may have to divide by 1,000. In case you have forgotten that, right? That's our way of going from milliliters to liters. Okay, so here's an example problem. Let's say I wanted to make a 2-liter aqueous solution that is 1.25 molar of CuSO4 5H2O. Okay, so the question is, how much of that copper sulfate pentahydrate in grams do you need to measure out to make the solution? Okay, so this is actually combining a couple of things here. First of all, your molarity equation, which is moles of solute per liter of solution. And also that molar mass is equal to, right, grams of something per mole of something, because it's giving us a mass of this CuSO4. Okay, well, that's what we're looking for. So we know we're going to need to use this equation in conjunction with this one. And our term here that's in both of them is the number of moles. So we'll see if we can't use that to our advantage. It gave us the molar mass up here is 249.71, so you don't have to worry about calculating that. Okay, so where do we begin? Well, let's identify what we want to solve for. We want to solve for grams. So I'm going to take this equation right here. Molar mass is equal to grams over moles. And we're going to rearrange that and solve for G, right? So multiply both sides by moles, and we're going to get grams are equal to molar mass times moles, right? Okay, well, molar mass is up here. We've got that, so that is right here. Moles, though, we're going to need to get using this equation. So I have to rearrange this guy on the left, this whole thing here, to solve for moles. So quite simply, moles are equal to, right, whatever your molarity is times the volume. The volume's got to be in liters. And so for this one, right, the number of moles, well, the volume is that's the molarity, 1.25 molar, okay, and the volume is 2.00 liters. Okay, so you have 1.25 times 2, okay, and that is, with significant figures, 2.50 moles, okay, of our substance. So now I have everything that I need. I've got the moles here to plug in. I have the molar mass up here. Okay, so how much stuff do you have to weigh out? Well, molar mass is 249.71 grams over moles, okay, and times 2.50 moles. So notice my units of moles there are going to cancel, right? I'm left with grams, which is what I want. So 249.71 times 2.5, and to three significant figures here, we're going to get the number of grams is 624 grams, okay, of CuSO4 5H2O. Okay, so there's an example problem for you. All right, let's do another one. 2.56 grams of silver nitrate is dissolved into 0.100 liters of water. What is the molarity of the solution? So same thing. We've got two equations we're going to need for this. Right, same one. Molar mass is equal to grams over moles. Okay, and that molarity is equal to moles over volume. So what do we want? We want a final answer of molarity, right? We want the italicized capital M. We want this. So we have moles over volume. That's the same. So we're going to need to plug in, right, some values here to solve for moles in order to get to our final answer. So what we're going to need to do is solve for moles by itself in this left equation. Well, that's going to be grams over molar mass, just using algebra to rearrange that. And that's going to be, well, 2.56 grams. divided by molar mass given in the problem, 169.88 grams over moles. Okay, and the number of moles involved here is, let's see here on the calculator, 0.0151 moles. And I'm just simply going to take that and plug it in right there. So my molarity is 0.0151 moles divided by my volume, which is already in liters, so that's good. I don't have to do any conversions. 0.100 liters of water. All right, and my molarity then is, right, just times 10 more or less, 0.151 molar AgNO3. Okay. Let's do another one, right? More practice. How much water is needed? So this is going to be a volume, okay, not a mass. How much water is needed to create a 0.25 molar solution with 42.65 grams of calcium oxide? Okay. So, and it gives us the molar mass of CaO up there. Once again, same equations. And this time I'm solving for V, right? And I'm going to have V is equal to moles over the molarity. In fact, let's just try a little shortcut here. Let's use more algebra. Let's solve the equation over here, this one, for moles, and let's plug it in just so we can see the variables in action, and that way we don't have to do two separate equations. So solving this for moles is, moles are equal to, right, grams over molar mass. And so if we take this and plug it in here for moles, okay, what we get is V is equal to, okay, on the top now, instead of moles, I've got grams, because that's what's left there. And on the bottom, I have molar mass times the molarity. The molarity stayed down there on the bottom. So just kind of skipped a step. We combined things. Instead of doing two separate math problems, we've done one. And now solving for V, okay, the mass given is 42.65 grams, right? The molar mass is 56.08. And the molarity it wanted was 0.250 molar. And so V is equal to 42.65 divided by the entire bottom. Make sure you put it in parentheses or you're going to get the wrong answer. 56.08 times 0.25. Okay, and with three significant figures here, the volume is 3.04 liters. 3.04 liters. Okay, so there's another type of molarity problem called a dilution. And this is actually one of the more frequently used things that we have to use as chemistry teachers, as we have to dilute stuff down. We make it less concentrated. By the way, the bigger the molarity, the more concentrated something is. So if something is very, very concentrated, you're going to have a high molarity. The closer it gets to zero, the more dilute it becomes. And oftentimes what happens is when we get chemicals, we get them shipped to us very, very concentrated. They do that because it takes up less space, and then we can dilute it down to the exact concentration that we want. Okay, so we get very, very concentrated chemicals. It's cheaper to ship them that way. And then we get to dilute them down to exactly what we want for class. So here's an example of a dilution problem. It says concentrated hydrochloric acid, HCl, can be purchased at 12.0 molar. That is stock solution HCl. Okay, this stuff is dangerous, right? 12 molar acid, that's going to hurt, right? You don't want that on you. However, the solution is too concentrated for lab work, right? I wouldn't let you guys mess around with that. It must be diluted. So suppose a 0.250 liter aqueous solution of 12.0 molar HCl needs to be diluted to 1.25 molar. So we're trying to cut it down by quite a bit here, to the point where it's a little bit safer to work with, right? It's roughly 10 times less concentrated. How much water must be added. Okay, so we're going to show you how to do this. There's a difference between how much water must be added and what is the final volume. Those are two separate questions. What is the final volume? The equation for this is M1V1 equals M2V2. All right, this is your dilution equation, and these should look like this. Apologies, it's undone my formatting. Okay, M1V1 equals M2V2, and this is saying that your initial molarity times your initial volume is equal to your final molarity times your final volume. Kind of a neat little trick with dilution problems. And I'll put this, well, let's put it up here. You do not need to convert volumes to liters, but you must be consistent. So if they give you milliliters in the problem, be consistent and use milliliters all the way through. This only applies for dilution problems. Any other ones on the previous examples there, you have to have it in liters. Okay, so you cannot do that to the previous type problems. Only here can you leave them in milliliters if it gives it to you in milliliters. So let's answer, actually, I want to do this question first. What is the final volume? And then 2, how much water did you actually have to add? Because those are two separate questions, and you have to pay attention to what the question is asking on your homework. So let's set this up. All right, let's figure out what is the final volume, which would be V2 here. Well, if I rearrange that equation, okay, I have V2 is equal to M1V1 over M2, right? That's just using algebra. And if I plug in stuff from the problem, my initial conditions, my initial molarity was 12.0 molar. My initial volume, okay, let's see, it was 0.250 liters. So it's given it to us in liters, so we're just going to leave it in liters. And my final molarity, okay, what I want to get it down to is 1.25 molar. Okay, so V2, let's grab a calculator here for this. We have 12, right, times 0.25, okay, divided by 1.25. Okay, and we get a V2, a final volume of, with 3 significant figures, 2.40 liters. Okay, so that would be answering question 1. What is the final volume, right? That's how much you actually end up with. But that's really not what's happening here. You're diluting it, okay, to some initial amount. You're diluting V1 into V2. So if it asks how much water must be added, which is, right, question 2 here, we have to actually subtract off whatever we started with. So if it asks, well, how much water did we really start with? Let's say here, added volume, added V. Okay, well, if we ended with 2.40 liters and we started with 0.250 liters, okay, that'll tell us how much you actually had to add to dilute this thing. 2.40 minus 0.250 with the right number of significant figures, that is 2.15 liters. Okay, so this is like answering question 2 here. So they are similar. Right, in order to answer question 2, if it does ask you question 2, you have to first do question 1, what is the final volume? You have to find V2 using your dilution equation. And then if it wants to know, well, how much did you actually add? Well, it wasn't 2.40 liters here. That's what the final amount was. You added 2.15. So that's your difference. Okay, so this last slide here is just a open space if we needed it, or if you guys needed it. But let's use it to solve a problem or two off of the worksheet. So this is off of your 6.6 worksheet 1 on molarities, the very first one, worksheet 1. We are going to look at example 1 out of the first section, and we'll try example 7 out of the second section. So the directions say how many moles are present of the solute in each of the following solutions. Well, number 1 says you have 100.0 liters. And we have a concentration of Na2S equal to 6.28 molar. Okay, So using the equations that we know, molarity is moles over volume, and that molar mass is, right, grams over moles, mass over moles. And this says, right, how many moles are present in each of the following. Well, this one is actually not even going to need this second equation, right? This first section, you don't need this, because we were already given a molarity, in this problem 6.28, and the volume is already in liters. So this first one, it's just simply got to solve for the number of moles. So we got to bring V up to the left side. And the number of moles then is going to be equal to your volume times your molarity. Well, that's 100.0 liters here, and your concentration is 6.28 molar. All right, to three significant figures, that is 628 moles of Na2S. That is a lot. Let's look at an example out of the second section. This time we are going to need both equations. How much water in liters is needed to create each of the following solutions? So it says we have 5.25 grams of NaOH. I'll save you a second and tell you the molar mass of that is 40.00 grams per mole. And that the concentration of NaOH is equal to 2.25 molar. Okay, so this time we will need both equations. Molarity is moles over volume. Molar mass is mass over moles, grams over moles. Okay, and we want to know V. So solving that for V is moles over molarity. But if we want to plug in for the moles here, okay, we're going to rearrange the right equation. So moles are grams over molar mass. And we're going to plug that in here. And we're going to have V is equal to the mass divided by the molar mass times the molarity. And that's going to be true for 7 through 12, right? They're all going to be solved using that. So V is going to be equal to here, well, the mass was 5.25 grams. Okay, the molar mass is 40.00 grams over moles. And the molarity given was 2.25 molar. Extend our line over. The volume with three significant figures here. Again, make sure the bottom is all in parentheses. This is 0.0583, and the unit here is liters, right? In case you're curious, just to make sure that you can convert that, that would be 58.3 milliliters, right? It wants it in liters, but to give you some idea, that is a reasonable amount, right? Imagine a 10 milliliter graduated cylinder filled up almost 6 times. Okay, so that's it for the first page there on your homework. Let's take a look at let's go to worksheet 2. Okay, so worksheet 2, let's look at problem 1. So these are dilution problems. Concentrated nitric acid, HNO3, needs to be diluted to produce 225 milliliters of 1.0 molar HNO3. If the initial HNO3 concentration is 5.00 molar, how many milliliters of it will be needed? Okay, so your equation is M1V1 equals M2V2. And we said previously, for dilution problems, we do not need to convert liters to milliliters, as long as we are consistent. So we don't have to do that here. So what are we solving for? Well, given a whole bunch of information there, 225 milliliters is the final volume, right? That's what you need to make. So that's going to be V2. 1 molar is going to be M2. And 5 molar is M1. So the one thing we don't know and what we're solving for is V1. So rearrange all of that. M2 said was 1.0 molar. V2, 225, let's make sure that looks like that, milliliters. We don't have to convert it to liters. Our answer is going to come out in milliliters. Right? We'll see the units cancel. Divided by 5 molar for M1. So your M's cancel. You're just left with milliliters as an answer. Okay, so this is really 225 divided by 5. And this is 45 milliliters. So that's how much you had to start with. That was what your V1 equals. Okay, so that is it for practice problems. You guys should work on worksheets 1 and 2 out of section 6.6 from this.